but the reads are interactive. It's when users, if they want to read the data, you want to serve the request immediately. And this is also streaming reads, means that you need to serve the request basically instantaneously. And there is a huge amount of read. Right. So for the Google file system, it's not user facing. It's actually a lot of work is done internally, so that the bandwidth is a favor over low latency. And for file systems, it's if you guys know the internet architecture, you may know that the internet architecture, the middle part is a TCP/IP. That is width for the internet architecture. So below TCP/IP, there are different types of technologies. For example, we can use Ethernet, we can use infinite band, we can use Wi-Fi, we can use 5G, right? Different technologies, but they are all okay to support TCP/IP. And on top of TCP/IP, those were tons of different applications, right? So it's only the middle part is at the narrow width. For those who are not very familiar, the IP protocol is trying to do the routing to find, given the source and destination, try to find the path to go from the source to the destination. And the TCP protocol is that try to decide the rate you can send so that the network is not congested. It's a congested control algorithm. Okay, here the file system is a narrow width. It sits between the hardware and applications. So the file system can run on different type of hardware, right? Those can be the even very traditional tape and the hard drive, SSD, right? Non-volatile memory, or not, it's okay, right? And the applications, it can support different type of application, from the traditional one to MapReduce, Spark, or all kinds of applications. So both the hardware and applications, they can change as long as the file system is the same. Right? So as for people on the top, right, writing applications, right, you don't need to worry about the hardware they use. Right? It can be the different type of storage, the devices, but you don't need to worry about those. And for a new technology, if it coming out, so that can also be integrated into the system, right? Without worry about what type of applications that is going on top of it, right? So this is the importance of file system. Okay, any questions here before we talk about file system? Okay, these are the Google file system design decisions. The first is that they store the files in chunks, right, to make them fixed size so that it is easier to manage and to scale. Right. Second is that how to do the reliability, that is through replication. Right. Each chunk is replicated across 3 chunk servers by default. So this decision choice is because for Google file system, they mainly use hard drive, and hard drive the cost is not very high. So they can trade the space for reliability. Third one, the single master node, as we discussed. The fourth one is no data caching. Right. So there's a large data set if you do at the stream node. If you do cache, and I think people use different ones. So the hit rate will be fairly low. Last one is that they do customize APIs, right? So that they can serve their own purpose. Okay, this is the architecture. So in this architecture, you will notice there are two types of arrows. The first arrow is very thick, so that is actually where you send the data. All the other arrows, those are very thin, the normal ones, those are the control message. The control message normally are very short, but the data messages can be very long because you actually send the data. Okay, in the system, you can see we have applications. The application have a Google File System GFS client. And the client will work with a GFS master. The master mainly maintains the file namespace. Basically tell, okay, you give me the file name, I can tell you the chunk and the location of the chunk. And the master also manages the chunk servers, which actually store the actual data. And they run the Linux file system. So between the Google file system, the GFS master, so they give instructions to chunk server and also check the state of the chunk server. So this part, the right-hand side is easy. Left-hand side, application, what they will do? They will first, the normal operation is that they ask about the file name and the chunk index. You may say the file name and the third chunk. Then the master node will return with a chunk handle, which is a sequence used locally, internally, and also the chunk location in the server. With this information, then the GFS client on the application can send using the chunk handle and also the byte range to the chunk server location and to request for the data. And the chunk server, once it receives the request, will send the data, which is the thick arrow here. So this is a basic structure. Any question here? Okay, the next one is that for single master to hold the metadata, right? The problem is that if this one fail, then we have the system fail down and also the scalability bottleneck. The solution for the first one, there are multiple shadow master nodes. Right? For the second one, is to minimize the master node involvement in all the processing. Right? The first one is that it never move data through the master. If you recall the previous the architecture, right? So the data is only done between the application within the client and the chunk server. Never went through the master node because the master node is heavily loaded already. Second is that they use a large chunk size to decrease the metadata. Right? If the chunk size decrease by half, then you probably will have twice of the metadata you need to process. Right? So that is bad for the master. That's why they choose a larger chunk size. But of course, the problem of choosing an even larger one will be, recall that a lot of the files are very small. If you use a very large chunk size, a lot of the files are much smaller than the chunk size. So you will see a lot of chunks are fairly empty. So that will decrease the utilization of the storage. So you see, here is a trade-off. Larger chunk size will decrease the metadata and increase the scalability of the system, but it will come with a lower storage space utilization. Okay, and the last one, the master node can also delegate to something called the primary replica in data computation. When you need to change the data, the master node will select one of the replica to do that instead of being involved directly. So this further reduce the overhead. And this one is a little bit complicated. Let's see how they actually do that in a couple of slides. Right. So for the chunk server, they hold the actual data. Right. They are free to join the league. This is very important because some server may go down and we may have some new servers in our back, right? So they are free to join the league. The system can afford that. So they store the actual data, they report the chunk location to the master node, right? And they check the integrity locally. Right? The metadata is just the namespace, right? And then also the map from the file to chunks and the location of each chunk. This is in memory, and it's fast and easy to access. So for the critical metadata, so this is a persistent local disk, and it also replicated to shadow master. They have the checkpoint down for fast recovery, right? Because the master node is really the weakness point for the system. Okay, now this figure is a little bit complicated. This is what I just described, the mutation, where you need to update the content of a chunk, right? For you to do. So for this one, because mutation is not rare, and it involves a lot of steps and overheads, right? So we want to minimize the involvement of the master node in this one, right? So to do this, so let's say here we have the master node, and we have three replicas, A, B, and the primary replica. So what we will do is that the client first send the step one to the master node, request I need to change something. Then the master node will reply to say, okay, so the master node select a primary replica. In this case, it's a replica in the middle. And then tell the client, okay, go to talk to this one, right, regarding the update. Then the client will also give the location of the replicas. Then the client will send the data to all the three replicas, the three chunk servers, and from now on, so you say only step 1 and 2 is with master node. But after that, it's after the primary replica will serve as a master node, right, to do all the management, right? So step 4, the client will talk to the primary replica instead of the master node to say, I need to update the chunk, right, for this one. The primary replica will work with the other replica, P and V, in step 5 and 6 to make sure they all finish update. And of course, the primary replica knows whether it itself finished the update or not. After that, it will go back to tell client, the 7, say that I will already finish update. Right? You can say among all the steps, master node only involved in 1 or 2. Right? But everything else is centered around the primary replica. We serve as a master node. Right. So also the control part and the data part are decoupled, right? The client, once it knows the chunk location from the master node in step 2, it sends the data to the 3 replicas, right? Without waiting for all those control information, right? So these 2 steps copy down 一 palette, right? Step 3